Here's going to be the last video of the semester, and it's all going to be about chapter 10, and I think I can fit it all in. What I'll do is, for the homework, I've just said read these sections. You can read the examples. Those are probably going to be good enough to get an idea of what's going on. But in the description of the video, I'll post some recommended homework problems to go through. But there's the idea behind this is we're going to be using our ways of analyzing statistics, analyzing these random variables. The random variables that we've been working with have been the population proportion or sample proportion and the sample mean. And those are the random variables we've been working with to kind of get information about actual population proportions, which are parameters, and actual population mean, which again are parameters. So how hypothesis testing works is you start with a given hypothesis. Maybe you have a proportion you're looking for and you know some previous information about it, and you start with that, and then you want to know if that thing still holds. So this is the idea. So we're going to start with a discussion about the language of hypothesis testing. And the idea is you're always going to have two hypotheses. And the first one we denote as H0. This is called the null hypothesis. And H1 is the alternative hypothesis. There we go. And so how we're going to go into our tests is we're always going to assume the null hypothesis. So we always assume the null hypothesis. And what that means is we treat it as a true thing. It's the way the world is. It lives according to this assumption here. And what we do is we analyze some data. And we weigh our possibilities. And what we do is we either accept our null hypothesis, in which case we would reject our alternative hypothesis, or we reject our null hypothesis and we accept H1. I actually like to think of it in these terms: we reject H1 or accept H1, because I like the idea of this is kind of the baseline of what we're assuming, and this is what's kind of challenging it. The H1 is kind of challenging it. Oh, should it be this? And then you either reject H1 or accept H1. But the hypotheses that we're going to be working with are going to be mutually exclusive. So you can't, so these basically mean equivalently the same thing. So these are logically equivalent. So an analogy you want to think is the courtroom trial. So we're all kind of used to the maxim that says, like, okay, you're innocent until you're proven guilty. So what's going on there is the null hypothesis is that a person is innocent. That's the way the courts kind of work, is you have that assumption of innocence. And then the alternative hypothesis is, wait, this person is guilty. And so you go through the trial, that's your analysis of data, And then it's determined either you accept H1 or you reject it. So you accept that they're guilty or you reject that they're guilty. And that's the same thing as accepting their innocence or rejecting their innocence. One kind of important wordplay thing is you don't declare their innocence. You don't ever find that they're innocent or find that they're not innocent, because that is the null hypothesis. That's what you're going in with. You either accept that they're guilty or you reject that they're guilty. So you kind of find that. Okay. So since we're assuming the null hypothesis is true, and in this situation, we're going to be talking about our H0, our null hypothesis, and our alternative hypothesis are going to be mutually exclusive. Like, a person can't be guilty and innocent at the same time. They have to be one or the other, not the same. Then we're going to have kind of this this matrix. I'll call it, I guess, the error matrix, where you have the reality of the situation. Either H0 is true, the null hypothesis is true, or H1 is true. If H1 is not true, then H0 is going to be true. So this is where it gets a little bit weird, because sometimes you might be thinking, well, how can we always know that H0 is true? We just assume that it's true. We assume that that's the only possible outcome. It's either this one, or if there's enough evidence to accept the alternative hypothesis, you then go with that one. It's very, very scientific in how it approaches things. So this is kind of where statistics goes a little bit outside of math, because math, you can prove things are true. You either prove them as true or not true. And there are usually a few more things. Here, you go with assumptions of truth, and then you kind of only move on to alternative things if there's enough evidence. But how it works is we have this matrix, either H0 is true or H1 is true. And this is how you can react. So if H0 is true, you can react by either not rejecting H0, which would be the correct conclusion, or you can react by rejecting H0, which would be what we call a type 1 error. So that would be an incorrect conclusion. All right, if H1 is true, again, you can not reject H0, which is not kind of accepting H1, which would be another type of error. That's type 2 error. And you could reject H0, which would be the correct conclusion. So again, thinking of it in our courtroom analogy, this is the person is actually innocent. And this is you don't reject their innocence, which is good. This is the person is innocent and you find them guilty, which would be type 1 error. This is that they're guilty, you find them innocent. Guilty, you find them guilty. So what we do here is we have probabilities set to type 1 and type 2 error. And they have names for the probability of type 1 error. We call that alpha. And we actually have a name for this. This is called level of significance. Level of significance. And beta is the symbol we use, so this is pronounced beta. It's just another Greek letter. This is what we use for type 2 error. And that doesn't have a special name like level of significance. Just a couple things about these is, So alpha is going to be called the level of significance. So if you hear us say level of significance, read it in the book, that's related to alpha. And as you're reading in the book, when you see the symbol alpha, that's also related to the level of significance. And that's going to be throughout the chapter 10. Okay, so what are some other things? Alpha and beta have an inverse relationship. Okay, so this is a little bit weird because what do we mean by probability of making a type 1 error? Well, this comes from the fact that you can actually never really tell the 100% reality of a situation. So unless you're there at the act of a crime, you're never going to know if a person is truly innocent or truly guilty. Even if you use, proof and evidence and things like that, there's always a chance that certain things can be contaminated. It's not exact. But what you can do is you can minimize making a type 1 error. And again, think about what's happening here. If you're making a type 1 error, that's when the person is innocent and you reject their innocence. How would you minimize something like that? Well, one thing you can do is you can make the requirements very, very hard to convict someone. So, for example, you have a jury of 12 peers, and you have to have a unanimous decision from the jury in order to convict, in order to make them reject the innocence of that person. So what you're doing is you're actually setting the probability that you make a type 1 error. So you're setting the level of significance. And actually, I'm going to write that down here. That's another point, is the level of significance is set before you collect data. And a lot of times it is all about kind of the stakes of the matter. So in our courtroom analogy, the stakes are pretty high because you don't want to convict innocent people. Now, so what you do is you try to make it very, very difficult to convict someone of a crime. And so you set that before the trial, and then you go through the trial, and that minimizes your type 1 error. Remember, again, type 1 error is an innocent person being declared guilty. So you minimize that beforehand. Now, what's this second point that I wrote down, or I guess the first point? The first point is that alpha and beta have an inverse relationship. So that's why I started talking about that. What does that mean? Well, what it means in this case is, again, think of what we had to do to minimize our type 1 error. We had to make it really, really difficult to find an innocent person guilty. Well, what effect does that have when you're dealing with a guilty person? Well, what you do is it actually makes it harder for that person to be convicted too. And if you don't convict them, you make a type 2 error. So that's what we mean by an inverse relationship. If alpha is going to go down, then beta, or if alpha is going to go down, if you want the probability of making a type 1 error to go down, then beta is going to have to go up a little bit. And if beta goes down, then alpha is also going to have to go up. Again, if you make it easy to convict someone, you're going to get a higher chance of having a type 1 error. So think about it in those terms. That's what we mean by having an inverse relationship. One goes up, the other one goes down. One goes down, the other one goes up. So for our purposes, when we're looking for parameters, or when we are kind of deciding which parameters to take, which parameters to leave behind, there are going to be 3 ways to set up hypothesis tests. And so the first one is going to be two-tailed. And the idea is your null hypothesis is always going to be that a parameter is equal to a value. And actually, that's always going to be the null hypothesis for any of these options. It's always going to be parameter equals a value. That's what we believe. We're always going to be using some previous information to believe that. And for two-tailed, our alternative hypothesis is always going to be parameter is not equal to the value. And then we have these one-tailed options, which are going to be our null hypothesis, parameter equals a value, and our alternative hypothesis is for left-tailed. Again, this is under the one-tailed. It's going to be that the parameter is to the left of this value. Or you have right-tailed, which is going to be that the parameter is going to be to the right of the value for your alternative hypothesis. So again, keep in mind that the two-tailed just means that your parameter could be either to the right or either to the left. That's your alternative hypothesis. Okay, so let's look at an example and let's translate some of the language. So here's the example. Suppose we have data from 2015 showing that 5% of Americans are vegetarian. We wish to see if this number has gone up. So what we do is we sample 1,000 Americans and find that 65 are vegetarian. So from our sample, we have that 6.5% of our sample is vegetarian. Is there enough evidence to reject our parameter from 2015? So what we've done is we've found that our sample is actually larger than the average American number, but what we have to do is we have to analyze if this would be a typical sample size. So that's the idea. So the analysis is we first want to figure out what our null hypothesis and our alternative hypothesis is going to be. And so our null hypothesis is going to be that the parameter we're looking for, the proportion of Americans who are vegetarians, is going to be equal to 0.05, right? So this is what we're starting with. This is what our historical records show. So we're going to say that this is the way the world is. And then someone's going to come along and propose, well, no, I think that the parameter is actually larger than that. Okay, so this is the setup. This is the game. We start by believing this. Someone makes a case for this, someone being our data, and that's what we're going to do now. So what we have is we're going to build a model based on our assumption. So we have that P is equal to 0.05, and we now want to look at the random variable p hat. So if we look at p hat and we look for the mean of p hat, Remember, if this is your actual parameter, then the mean of p hat is going to be the same as the actual parameter. And when we're looking at p hat, what sample size are we using? We're using n equals 1,000 because we're thinking in terms of all sample sizes of Americans that are size 1,000. And what we want to do is we want to determine if our sample size is typical. Okay, so we have n equals 1,000. This mu of p hat is 0.5. And we can figure out the standard deviation of p hat. Remember, that looks like this. P times 1 minus p over n, which is going to be the square root of 0.05 times 0.95 over 1,000. One thing to keep in mind is because we're assuming that this is true, because we're assuming this is the actual parameter, we can use it in place of the actual parameter. We don't have to use the 0.065 as our best guess because we're in a world where this is true. All right? So that's going to give us 0.00689, or I guess about that. I rounded it off. And then what we're going to do is we can assume p hat is normally distributed. And why is that? Well, our population is all Americans, and our sample size is 1,000. And so you can think, well, that's definitely less than 5%. So we have independence. And then what else do we need to check? Well, we do need to check that n times p times 1 minus p is greater than or equal to 10. And so you use 1,000 there, you use our p there, and 1 minus p, and you can compute this number and show that it's actually greater than 10. So I'll let you do that. Okay, so we can do that, and we can build kind of a normal model where in the middle you're going to have 0.05 because this is our assumption of what's true. And then if you go out plus the standard deviation, you're going to get to 0.05689. And if you go back a standard deviation, so minus that, you're going to get 0.04311. So this is kind of a model for this. Okay, and then our point estimate is going to be that p hat is 65 over 1,000, which is 0.065. And if we were to compute the z-score of this, well, remember, if we compute the z-score, that's just going to be this point estimate minus the mean of this distribution divided by the standard deviation. And so you'll get 0.015 divided by 0.00689, which will give you about 2.18. Okay, so what I'm going to say is we're actually going to use this to reject our null hypothesis. And so why is this good enough to reject H0? So this is the question. Well, maybe on the outset, it's actually not good enough because we haven't decided kind of a level of significance. We haven't decided what it would mean, what would be good enough for us to reject our null hypothesis. But traditionally, if your sample mean or your sample point is more than 2 standard deviations away, then we generally think of that as what's called statistically significant. And so this thing, 2 standard deviations away from our sample mean, or our sample proportion, that's going to be statistically significant. And so there are 2 ways to read this. So what I'm going to do here is I'm actually going to kind of build my model again. Here I have 0.05, and then here I have like 0.065, somewhere over there. And so this is p hat. And if I z standardize it, I'm going to come over here to 2.18. And one way you can look at it is we can say, well, the first interpretation is going to be that p hat equals 65 over 1,000 is too many standard deviations. To the right of mu p hat. And in this case, that's going to be 2 standard deviations away. All right? And that's exactly what it's telling you here, that you're 2.18 standard deviations away from this mean. And so you can say, well, that actually seems pretty significant, and that's why we call it statistically significant. The other interpretation is you can figure out, well, what's the probability that our sample size is actually going to be that value or above. And that's going to be the same as, so this is the second interpretation, as the probability that the z-score we get is above 2.18. And if you go and you look at table 5, you'll find that this is 0.0146. And so this area here is equal to 0.0146. So this is sometimes called the p-value. And this interpretation uses p-values in order to accept or reject your null hypothesis. And so what this is saying is that the likelihood of getting a sample size that's going to give you an estimate of 6.5% is actually very, very small. It's, between 1 and 2%. Or if you want to think of it like this, if we were to take 10,000 samples of size 1,000, only about 146 of them would give you this parameter. So that's pretty small. And so again, what we're saying is, since the area under this curve, or the probability that our sample size is going to be that or above, is very, very small, we're actually going to reject the null hypothesis. Because what it's saying is, if the null hypothesis is true, this is highly unlikely. So it's like flipping the coin. If flipping a coin is actually 50%, it's going to be highly unlikely that you're going to get 5 heads in a row. So the assumption or the critical thinking analysis you're going to do is, oh, well, maybe something is wrong with that coin, or maybe my friend is lying to me, or something like that. So this is the idea. And what we get here is, this is again part of interpretation 2, i.e. if the probability of making a type 1 error, which is equal to alpha, is greater than the p-value, then we reject H0. And so it's typical to use alpha equals 0.05. So in this case, what we've done is we've found that alpha, which is equal to 0.05, is greater than 0.0146. And so what we've done is we're going to use this level of significance to reject our H1. So what does rejection of H1 mean? It means that our new frame of reference is there's enough evidence out there to believe that the number of vegetarians in the United States is higher than it was in 2015, or at least the proportion is going to be larger. All right, so again, the idea is that if our kind of sample statistic is highly unlikely, then what you do is you use that to kind of adjust your frame of reality. So you start with something like your null hypothesis, and then you set your level of significance. And I know in that example we didn't set the level of significance until afterwards, but again, it's generally acceptable if the stakes are pretty low. And why would you be studying the number of vegetarians in the United States? Maybe you work for a food distribution company and you want to know what foods you should be distributing. Maybe it's not life or death, it's just profits of your company, and you're not, well, you should be worried about that, I guess. But again, it's not life or death, and there are, consequences to setting your level of significance too low. Again, like I said, it inversely affects the beta value. So you want to keep that in mind. So you don't always want to set it super low. So we generally set it about, at about 5% or 0.05. So again, you set your level of significance. That's going to be the probability of making a type 1 error. And we have kind of these two pictures. So how you want to interpret that alpha is here you have your given parameter, that it lives here on your distribution of p hat is part of the null hypothesis. This follows from the null hypothesis. And you set this up, and you have this area region that's equal to alpha. And so this is one-tailed, but this is actually technically, this picture is going to be right-tailed, like the last example. If it was left-tailed, then that critical area or critical region would be on the left. So you look at that, and you do your analysis, and if your p hat is here, that's going to be like our last example, and you're going to reject your null hypothesis. But if your p hat is here, you're going to accept the null hypothesis. Because in that case, well, it still represents kind of a typical value, a typical sample that's kind of bouncing around this. It's very close to that. And the two-tailed response, or two-tailed setup, is, well, again, you have your p there. This stems from the null hypothesis. And the idea is, well, the new value, or the alternative hypothesis, is proposing that the new parameter is actually possibly on either side. And so how you set that up is your critical region is actually going to be on both sides. So this is going to be your alpha there. And so again, if your p hat lives kind of not in that critical region, you're going to accept your null hypothesis, because this is still a very, very likely value for the proportion. And then if the p hat is outside, this is where you reject it. All right. So this is generally the setup. And again, it still just boils down to this idea, is our sample size highly, highly unlikely in the world where your parameter is assumed to be this? And if it is highly unlikely, then you adjust your perceptions, what's actually going on. Okay, so we're going to do one more example. And so this is example 2. And it's going to be about hypothesis testing for a sample mean. But the outset is going to be the same. You're going to have your null hypothesis, which is going to be the way you think the world works, either based on some historical data or based on something else. And then you're going to take a alternative hypothesis to it, collect your sample data, and you're going to determine, based on that sample data, if the world in which your assumed thing makes that sample data possible or not. So what we're going to do is, we have this example. It's about donuts. You guys probably think I eat a lot of donuts. I do. In 2008, it was estimated that 1 billion donuts were consumed by Canadians. I was reading online about how Canadians are like the top donut eaters in the world, which is pretty cool. So Canadians, and the population in Canada in 2008 was about 33 million. So that gives an average of 30.3 donuts per Canadian per year, or at least for that year. Okay, we wish to study if this value is still reasonable. We sample 50 Canadians and we find that they eat a combined total of 1480 donuts with standard deviation of 5 donuts. Does this indicate that the number of donuts a typical Canadian eats per year has changed since 2008? Okay, so one thing to note when you start the solution is since we are working with X bar, we use t distributions. So you're going to see that come into play as we work out this solution. But before we even start with that, we want to set up our hypothesis test. What exactly are we doing? Well, what we need to do is set our null hypothesis, and that is always going to be that a certain parameter is equal to its value. So this is going to be that our parameter, which is going to be mu, it's going to be some population mean, is going to be equal to 30.3 donuts. And this is the null hypothesis. This is what we're taking historical data into, and we're saying, all right, the typical, maybe I guess it should be donuts per year. Typical Canadian eats 30.3 donuts per year. And then what is the alternative hypothesis? So now you have to think, is this a two-tailed thing or a one-tailed thing? Well, we're not asking if the number of donuts has increased, and we're not asking if the number of donuts has decreased. We're just asking if it's changed. So our alternative hypothesis is that the typical number of donuts a Canadian eats per year is not 30.3. So this is a two-tailed hypothesis test. And so the idea is, well, how we're setting this up is we are using X bar, and we're using a sample of 50 Canadians. And so what we can assume is that the distribution of X bar is normal. Why can we assume that? Well, we have two things to check. Since we're working with the sample mean, we just need to make sure our sample size is greater than 30, which we're working with 50 greater than 30. And we also have to make sure that the sample size is less than 5% of the population. Well, population of Canada right now, we're not given, but we can assume that it hasn't changed so much drastically from 33 million that 50 Canadians are not 5% of the population. Let's hope not. That would be a very dire situation. I don't think worrying about donuts would be a top priority. So we're going to assume that this is less than 5% of the population. All right. So we can assume our distribution of X bar is going to be normal. And remember, we haven't gone to the t distribution yet. So this is in fact normal. It is the distribution of X bar. And what do we know? Well, we know that the mean, it doesn't matter what number your sample size is, the mean is always going to be equal to the mean, which we're going to assume is 30.3. And this is, again, the null hypothesis. So the reason we're assuming that is there. All right. So from our sample, if we use our sample, we had, what did we find? We found that $14.80 donuts were consumed by 50 people. And if you make this computation, you get 29.3 0.6. And so I'm going to be over here, 29.6. So it's going to be somewhere there. All right, what haven't we done yet? Well, we actually haven't decided our critical region yet. So what I'm going to do is I'm going to say, let's use alpha is equal to 0.05. So again, what this is saying is this is the probability of making a type 1 error, and it's the level of significance. So this is what we want to set it at. Okay. So what does this mean? That means that if we look at our x bar and we have our mu x bar there, since we're working with a two-tailed experiment, we have our two tails here. And this is going to be our value alpha. And so what this means is that each one of these is going to be equal to 0.25. Because you want to split that region in two. So we have two tails. All right, and what we want to do is we want to see, well, does this value live, I guess, on this side or on this side? So this is going to be our sample of 29.6. Where does it live? Okay, so now we have to use t-distribution. Why do we have to use t-distribution? Well, because we do know this, but if we try to compute the standard deviation of x bar, you're going to see that that's going to be the standard deviation of our actual parameter divided by square root of n. We don't know this. And so what we have to do is we have to estimate this by our sample standard deviation divided by the sample size, take the square root of that. And if you do that, you're going to get 5, remember, 5 donuts. And then this is going to be square root of 50. And what you'll find is this is 0.7071. And so what we have to do is, instead of using the z value, we have to use the t value, which again is just going to be our x bar minus the mean divided by our approximation of the standard deviation. And the distribution of this, remember, distribution, not normal, but still usable, I guess. I don't know how to spell usable. Doesn't matter. Okay, so what does that mean? Well, what it means is we have computations, our t distribution is still going to kind of be symmetric and look something like this. And it's still going to have a mean of 0 when we look at the t value. And we're still going to get that the area under the curve is 1. And when you transfer the critical regions, well, the critical regions are still going to be, you know, in these places. And this critical region, we still want it to be 0.025% per 1. And what we want to find is we want to find that when we change this t value, does it live here or does it live here? Because we know it's going to be to the right or left of 0. Sorry, left of 0. All right. So what do we have to do? We have to figure out what t distribution we're working with. Well, which distribution do we have? Well, our distribution is going to be determined by your sample size. Distribution for n equals 50 is going to be, well, the degrees of freedom are going to be n minus 1, or 50 minus 1, which is 49. And what you can do is you can look up on table 7 in the back of the book, and it gives you a distribution list for degree of freedom equals 40 or degree of freedom equals 50. And since 50 is closest to our value, we're going to choose that one. And you're going to see in this example, you know, it makes sense to still use that. If you found the t distribution for 49, it would still give you very, very close numbers to this. Okay, so what we do is we make this computation, and you're going to get negative 0.9900. And what you do is you go and you look at what the alpha value is, or I guess the area in left tail to this value. And this is going to be, again, from table 7. And this is where you're reading from the degree of freedom equals 50. And you find that this t value is going to live when the area is between 0.20 and 0.15. And it's going to be to the left of this value. So what does that mean? That means that where our t value lives, it's going to be here. So this is negative 0.9900, because to the left of it is going to be a value that's between 0.20 and 0.15. So this is a dash. This is between. So between and. So what that means is, if I look at this actual area here, this area is going to be somewhere between 0.20 and 0.15. And since that area is greater than this value here, greater than that critical value, what you're going to do is you're going to accept null hypothesis. because this sample is close enough to your mean to still be typical. So this is going to be your sample. It's going to be somewhere over there. It's not in that critical region. So we, again, accept the null hypothesis. So again, it seems reasonable to expect that the number of Canadians, or the number of donuts that a typical Canadian eats each year is still 30.3. And I do want to warn you, I pulled those numbers out of my head. I did, some initial searches on the internet to make sure that they were reasonable. But don't go to your Canadian friends or relatives and be like, you guys eat so many donuts. I learned that in my stats class. Because these numbers might not be real. Anyway, so that kind of wraps it up for hypothesis testing. Remember, again, the idea is you build a model based on assuming a certain parameter, and then you take your sample size and you see, does this sample size indicate that that setup is unlikely? And that's how it works. Let me see if I can grab my cats so they can say bye to you. So here's Nobody. She actually wants up on my shoulders. She does this a lot. Yeah, she's trying to learn about hypothesis testing now. And then William Blake is sleeping over there. So I'll just capture him so he can say bye to you. Here. William Blake. There. It's like, okay, I want to go back to sleep. All right.